Hi, everyone, and welcome to the first of our keynote talks today. And we have the pleasure to have Galvina from Quantum Machines, and looking forward to his talk. So, Gal, the floor is yours. Thanks.
Thank you. Thanks very much. So let me just present this screen here. And I think you should be able to see my slides now. So hi, everyone. Good afternoon, good evening. For us, it's already quite late evening at the moment. I'm in Tel Aviv. My name is Gal, and I'm a physicist working for Quantum Machines. And today I want to tell you a bit about the company and also about what it's like to work in the quantum industry in these exciting times. So let me begin by telling you something about who I am, about some background. I'm an experimentalist. I did my PhD building cold Rydberg atom systems, which involved some quantum optics as well. And during my PhD, I built, this is one system that I built, and this is another. This is what an optical table looks like inside of the lab. And here, it's a younger, more vibrant me winding some coils on a lathe. So building quantum systems in the lab involves doing a bunch of different things. So there's a mechanical design, there's optical engineering, there's design and construction of ultra-high vacuum systems. There's a lot of plumbing, more than you'd expect, because you need to connect things up and you need to cool things. And for example, these orange things in the sides are coils carrying large currents. So you need some cold water to run through them to get them in working order. And apart from that, there was programming, things like data processing and designing real-time experimental control systems. And also, at the end, maybe there was some time to do physics. And other than that, I really love scientific outreach. I've written many popular science articles, but almost all of them are in Hebrew, so maybe that's less relevant for this audience. So like many experimental PhDs, I wouldn't say I'm a real expert on anything in particular. I've done lots of quasi-professional tinkering, which in my eyes is what an experimental PhD is. I'm a jack of some trades and a master of some trades. That's me. And who's Quantum Machines? Quantum Machines is a company of quantum physicists and engineers, and we're on a mission to revolutionize quantum control and unlock a new era in quantum research. We have almost 80 employees, including experimental physicists with backgrounds in all quantum platforms, superconducting, semiconducting, quantum dots, NV centers, cold atoms, and more. And we have brilliant engineers and programmers as well. But everyone and everything that we do is focused on quantum control. We do nothing else, and we are absolutely a quantum control company. The company is about 3 years old now. We have customers in dozens of countries, from leading academic labs to major enterprises. In academia, many of the prominent universities you could name are customers, and in industry, many of the most visible players in the commercial quantum world are customers as well. All right, so what's quantum control? How do you run a quantum experiment? Well, quantum computing or any quantum technology is about more than just a quantum processor. In order to control and measure a quantum system, we need to send pulses and detect and measure the pulses that come back from the system. So we need some way to interface the classical signals with the quantum systems. It's not just one classical signal, right? It's typically something that looks a lot more like multiple signals, a bit like an orchestra. So in reality, typical experimental setups consist of lots of different instruments, and almost all of them were developed for other purposes. And you need a way to synchronize and control them, to orchestrate the experiment. And this is how things have been done for decades. Right, but at some point, you just hit a wall, and experiments become either impossible in principle or extremely demanding in terms of the effort and time invested in the infrastructure bring up. People have started to realize that real quantum experiments, or quantum control, isn't going to come from some generic electronics repurposed for quantum experiments. So whether the goal is next generation experiments on quantum dynamics in an academic lab, or scaling up quantum processors to realize full-blown quantum computers, we need a ground-up rebuild of our quantum control infrastructure. We need a quantum control system that's designed from the ground up for quantum. Okay, so our instruments, the old instruments, have taken us very, very far, but now it's time to take off, and that's what we're here to do. Okay, so we need a new control paradigm, and this is what we call the Quantum Orchestration Platform. It's an integrated hardware and software system that can run the most complex multi-qubit experiments out of the box, with no need to synchronize DACs and configure FPGAs. We need a system that's scalable, and most importantly, we need something that you can interface via a language that is intuitive. And that is the Quantum Orchestration Platform, or the QOP. So at the heart of our solution is a chip architecture that's specifically designed for quantum experiments. And we call this chip our pulse processor. And the pulse processor enables generating RF and microwave pulses in a fully parametric way. This means that our pulses are synthesized on the fly. It's not a waveform that you upload to a signal generator beforehand. It's something that you calculate one clock cycle at a time. The pulse processor also needs to be able to acquire and manipulate input pulses. There's a rich mathematical library that includes everything from arithmetic through trigonometry and other mathematical functions. There's even neural network activation functions that you can run on the fly. And also, you need to be able to run complex control flow, so things like while loops, for loops, conditionals, and we even support switch cases. And you need to be able to do all these things such that they scale over multiple qubits. All of this is controlled from our programming language Qua, which I'll show you a bit of in a few slides, and is compiled for the pulse processor through our compiler. Right? So we have a language, a compiler, and a chip all rolled into this platform. Okay, so this real-time approach, I said before that we don't upload waveforms to an AWG. We synthesize the pulses on the fly. And this real-time approach, besides making it possible to run experiments which are otherwise not possible, and opening new avenues for quantum control, it also substantially reduces runtimes for experiments in comparison to how they were performed with other tools in the past. This is an example from a customer at the Lawrence Livermore National Lab in the US. It's an experiment called a two-dimensional Ramsey measurement. And it's not a very revolutionary experiment. It's a calibration that's been done for years. But with a pulse processor, it becomes a lot quicker. Right? So this is how things have been done in the past. This type of measurement would have taken them about 900 minutes. And with the QOP, we cut it down by a factor 450 to get it down to just 2 minutes. So how did this happen? How did we get this amazing speed up? So first, maybe I need to tell you what the Ramsey experiment looks like. So it involves two pulses that are separated by some delay time. So you play a pulse, you delay, you play another pulse, and then you perform a measurement. So in this pulse, the x-axis is the delay between these two pulses, and then the y-axis is the frequency of the pulses. So the first speed up comes in comparison to generic test equipment, comes from the fact that the pulse processor generates the waveforms on the fly in real time. So with a traditional AWG, each point on this plot is its own experiment, and you need to define and upload a different waveform. And this results in a heavy communications overload between the experimenter's PC and the test equipment. But with the pulse processor, all pulses are generated on the fly according to instructions. So no waveform has to be uploaded beyond a simple template, which then the pulse processor can manipulate. It can stretch it, delay it, change frequency, and do many other things. Then a second speed up comes from the ultra low latency feedback. So that means that we're able to measure the system and respond. And we do with this capability, we can do something called active reset. So what does active reset mean? So with a typical qubit experiment, you have to make sure that the qubit is at the ground state when you start the experiment. So maybe if you've done, this is the first step of an experiment, that's easy. It's probably at the ground state more or less. But if it's a step somewhere in the middle, maybe the qubit is still at the excited state. So you need to be able to do something. Traditionally, what people have done is just to wait for many T1 times, so many relaxation times of the qubit, to wait until the qubit has definitely decayed. And even if you do that, it's not perfectly good, because due to the finite temperature at which this qubit lives, there is some thermal population. So the qubit is not perfectly at the ground state. But what active reset does is that if you're able to measure the qubit, determine its state, determine that it's in the excited state, and then play a pulse to force it down into the ground state, then you can be sure that the qubit is the ground state, and you can do it very quickly. So active reset cuts down further from this 15-minute mark down to a 6-minute mark. And there's some other nice tricks that you can play, but maybe we don't have to go into everything right now. Okay, so how does this look in the lab? What does the quantum orchestration platform look like? The first lowest level of this stack is the quantum side itself, the QPUs, the qubits. So if it's a superconducting qubit, then maybe you have a dilution refrigerator with a qubit. Maybe you have a few. Then on top of that, you have our hardware. This is our product, the OPX, or Operator X. And the nice thing about this platform is that you are able to scale it very easily. Maybe if you have just one qubit, you need a single OPX. If you have many, then maybe you need a few. And this system is built to be able to be stacked and synchronized. And you don't need to think about the system or program it any differently if you have one OPX or if you have many. Okay, on top of that, there's some server that connects to the devices. And at the end, there are client computers that can be connected through it via network or remotely via the cloud. Okay, so let me now teach you some Qua. It's one step further in the process. It's a very simple language, and I think you will find that many of you have already speak Qua to a great extent. Okay, so this is a Qua snippet. And what it does is to run a simple experiment to measure the T1 decay time of a qubit. So it's measuring how quickly the qubit goes down from the excited state to the ground state. So it's a for loop. Okay, so this is code that runs on. This code is written on the client PC. It's then compiled and then sent to be run on our hardware at real time. Okay, so although it might look like Python code, which is a good thing because it means it's readable, it actually runs on the FPGA on the chip that lives inside of this box. So we have this for loop. So you are able to run the experiment many times on the chip. And inside of this for loop, we have a second loop that is going to be scanning some parameter tau. Okay, this is going to be a time delay. Then we see the next thing is this is a pulse level programming language. So we're playing some pulse, but we're able to do parametric operations on it. So this is one parametric operation. This is taking the pulse and stretching it vertically, changing the amplitude of the pulse. And this is a different parameter that's stretching the pulse horizontally in time. It changes how long we're going to be playing that pulse. Then we have this wait statement. So I told you before that waits between the pulse. How long are we going to wait until we measure the state of the qubit? Okay, so this is another parametric pulse. And then we perform a measurement. Okay, so this measurement gives me the state of the qubit. It does some technical things that are relevant for superconducting qubits, a demodulation, if somebody in the audience is familiar. Any questions, by the way?
Gal, sorry,
Yeah.
they're writing in chat also that the slides, we cannot see the slides. I don't know what is going on. I'm trying to contact Araceli, but just to let you know, that we cannot see the slides.
So the whole 15 minutes, you could not.
No, I think it was about the last minute or so. Maybe Araceli can help.
Okay. So maybe we can jump back a few slides. I don't know what the last thing that was seen, and I can't see unfortunately, I cannot see the chat.
Okay, can you stop sharing and sharing again? I didn't see any issue, but thanks, Lorenzo.
Yeah, thanks.
Yeah,
so I stopped. Cannot present while a question is shown on stage.
Oh, somebody. Okay, can you try again?
Sure. Yeah, absolutely. So let's try. Oh.
Maybe it was that the question was shown that stopped there.
Okay. So I don't know where we stopped, and I can't see the questions, unfortunately. So I guess I'll just jump back to showing you Qureca. Okay. So.
Thank you.
Okay, great. So this was a snippet of a bit of an experiment. I can just quickly say again what I said before. The key point, the take-home message is that this code runs on the hardware at real time and is able to generate pulses parametrically. By saying a parametric pulse, what I mean is that you can modify it on the system at real time. And maybe the most interesting thing here is that I'm able to measure the state of the qubit. I'm able to compare a variable, a real-time variable that I've populated from a measurement to some value. So this is doing some mathematical operation. Run some loop, and only if that state is true, only if the qubit is in the excited state, then I play a pulse, right? So this is exactly feedback. I told you before about this active reset stage, and this is exactly it. So I've performed the measurement, and only if the measurement says that the qubit is excited, then I play a pi pulse. So it might seem a bit trivial, but doing this with traditional tools is pretty much impossible, and doing it quickly with traditional tools is absolutely impossible. So we're able to do this type of operation with 100 nanosecond latency or thereabouts, meaning the system waits less than 100 nanoseconds until it reacts. This is crucial if you want to be working with qubits because their coherence times, their lifetimes, are measured in hundreds of nanoseconds, microseconds, depending on the qubits that you have, or more. Okay, so because this is a career event, one question I wanted to answer is what kinds of tasks are done at QM by technical people. Okay, so I want to separate it to work for physicists and work for other engineering disciplines. And I mostly do this breakdown because I'm a physicist and I'm more comfortable discussing that. But I'm happy to answer questions if there are no non-physicists in the audience. Okay, so physicists at Quantum Scene generally fall into one of these categories. People either do hardware development. So hardware development means characterizing the needs of customers, identifying the directions that the industry is going, assisting in the selection of components on the front end, meaning the analog components connected to the qubits directly, and directing the development of custom devices, new products, new running prototypes, and many other things. This is one side of the work. Other than that, this is something that I am highly involved in. There is software development. So that means developing Qureca code, implementing tools for our customers, and supporting our open source community. We have a few open source repositories where we develop software for the quantum community and for QM customers. There's quantum algorithm development. So that means implementing various quantum protocols in Qureca and otherwise identifying how the language is suitable for running the next generation of quantum experiments, building quantum simulators that solve time-dependent master equations and trying to understand the underlying physics better. And finally, one of the most important pieces of work at QM is to help our customers do amazing science. this is a department at QM that is called Customer Success, and it involves participating in demonstrations to potential customers, reading academic papers, and providing technical knowledge of customer physics and use cases, helping diagnose and solve customer issues, helping to develop customer-tailored solutions, many other things. We take great care and a lot of pride in how closely we work with our customers, something that the company is very proud of. Okay, what about non-engineering roles? So there's many. More than half the company are non-physicists. More than half the R&D in the company are non-physicists. So there are electrical engineers that do things like analog design, board design, front-end design, making sure that the outputs are quiet and perform well and run at low latency, etc. There are RF engineers that do things similar to what I said before, but are focused on generating pulses at the radio frequency, meaning megahertz, or microwave, meaning gigahertz frequency ranges, which are needed to interact with qubits. There are engineers doing digital design. So these are the people designing the chip, the pulse processor, and doing verification that it actually does what it was designed to do. Software engineers do things like language design, compiler design, and doing embedded programming, because there's a lot of embedded systems programming in our various products. And there are, of course, algo engineers that are doing things like digital signal processing, for filtering, and for designing more clever ways of working with the data. And there are also people from a software background, pure software background, that are doing quantum algorithms and designing compilers from higher level languages above QA down to the QA level. Okay, and what's it like working at QM? So it's a high tempo environment. One of the things that impressed me most before coming to the company was that after 10 months of being afloat, of existing, there was already a first piece of hardware on a customer location, which is an amazing feat. And there are loads of features being developed all the time, and we have many next generation products on the way. There's a lot of variation from day to day, so you could be finding yourself working on physics, say, if I'm a physicist, but also doing software design, tackling some electrical engineering problems, and also working with customers, which is always very challenging, and you can learn a lot from it. And there's a big community of people to learn from. So again, if you're a physicist, physicists are generalists. I said that in the beginning, that like you're a master of no trade and you're a jack of many. So sometimes we do good enough software development. Sometimes we do good enough circuit design. And at QM, working for a big company or working for a company with other engineers, there's an amazing chance of actually learning how these things are to be done professionally when you grow up. So it's very fun, it's very challenging, and I invite you to join us. This is the vision of having some data center filled with our products and controlling a big, large-scale quantum computer. Just reminding you again, it's a company built for quantum physicists, by quantum physicists, for quantum physicists, and driving all your experimental dreams. Okay, so saying again, all our teams are hiring, whether you're an engineer of any discipline, and non-engineers as well, actually. Check out the careers page. I thank you for your attention, and I hope this was helpful. I'm happy to take questions.
Thanks very much, Dan. Very, very nice overview of what you're doing in quantum machines. I'll just take one question. We are running a little bit late, but how can undergraduates get involved with quantum machines?
Well, we have an internship program that's been very successful. We've taken quite a few interns in the past couple of years since I've been in the company, and you're more than welcome to email me. We have internships ranging from 13 weeks. We've had a person coming for 6 months and more.
Great, thanks. Okay, I guess if there are some other questions, people can directly chat with you or any other of the other people from Quantum Machines in the booth later on. Again, thank you very much, Gal, for the talk, and a pleasure having you here. And see you soon.
Thank you. See you soon.
Thanks.
Bye-bye.
Bye.